Now we will talk about the normal Zeeman effect. The energy levels of electrons within an atom will be affected by the presence of a magnetic field. So this leads to the Zeeman effect, and we have two types of Zeeman effects, normal and anomalous Zeeman effect. So we will see when we have the normal Zeeman effect and when we have the anomalous Zeeman effect. So the first thing to note is that the energy levels of electrons within an atom are altered by the presence of a magnetic field. H. Okay. So as I said, we have two types. So if we have no net spin angular momentum, that means the S value should be 0. This is going to lead to normal Zeeman effect. On the other hand, if we have a net non-zero spin, this will lead to anomalous Zeeman effect. And actually the anomalous Zeeman effect is the more common one, but first we will talk about the normal Zeeman effect. And in the Zeeman effect, the amount of splitting of the energy levels is proportional to the magnetic field H. So magnetic field H controls the amount of splitting. And here you can see a diagram for the normal Zeeman effect. So for a transition between S and P orbitals, so you can see that L equals to 0, we have the S orbital, and then we have L equals 1, P orbital. S orbital has no net orbital angular momentum, so L is equal to 0. Square root L plus 1 would be 0. So we would find that L, which is square root L plus 1 H bar, is 0. On the other hand, the P orbital has an orbital angular momentum, which is square root L plus 1 H bar, that is equal to square root 2 H bar. So we will see splitting of the L equals 1 P orbitals into 3 for the magnetic quantum number m sub L equals -1, 0, and +1. And we're going to see that the splitting of these levels, the delta E between these, will be the same. So in the normal Zeeman effect, we have equal splitting of the energy levels. And the way to detect this splitting is by looking at the absorption spectrum of these atoms, or emission spectrum. So we can detect the transitions from P orbitals to S orbitals. So initially we have L equals 1 to L equals 0 with no magnetic field, we would see basically only one spectrum, and for magnetic field greater than 0 we would see three peaks in the spectrum that correspond to transitions from m sub L equals -1, 0 and +1 to the s orbital level. Okay, so I would like to account for this splitting now. So the way I'm going to do that, I'm going to use a semi-classical model. So let's recall when I put a magnetic dipole moment inside a magnetic field, the energy of a magnetic dipole moment M in a magnetic field H this is given by the following expression. The energy of the magnetic dipole moment is minus mu0 permeability of free space dot product between the magnetic moment and the external magnetic field. This is in SI units, or we can write this in CGS units, minus m dot h in CGS. So here mu0 is 4 pi 10 to minus 7 Henry per meter. Magnetic dipole moment is ampere meter square. H is ampere per meter. And in CGS, the magnetic dipole moment is measured in electromagnetic units, and the magnetic field is in Ørsted. And we find the energy in joules in SI and ergs in CGS. So we remember this relationship. Now, I want to go back to our classical model. I also recall that from our classical model, we had for the magnetic moment in the z direction, m sub z, was current times the area, where the current was given by EV over 2 pi r. It was the charge that flows in one period, E divided by T. So we're talking about the electron that's orbiting around the nucleus. So we see that this is actually, if I use the absolute value for the charge, this is actually minus absolute value of the charge E, V over 2 pi r. That was the current. So the corresponding magnetic moment, mz, I would find current times the area. It's EV over 2 pi r times the area of the loop, pi r square, and that would give me, using the correct sign here, minus E VR over 2. I would see the cancellation of pi and one of the r's, so I would get at the end EVR over 2. So that was the magnetic moment. Now about the orbital angular momentum. For orbital angular momentum, we can write using quantum mechanics. You're using the fact that orbital angular momentum is quantized. So we can write mvr, mass of the electron, times its velocity times the radius of the loop, is equal to m sub L h bar. So it was quantized in units of m sub L, which tells us that the tangential velocity is m sub L h bar divided by mass of the electron times r, the radius of the loop. Then we can write the energy of the magnetic dipole in the magnetic field as minus m dot h. So I have minus mu 0, let's do it in SI, m dot h, and this would give me minus mu 0. For the magnetic moment, I have minus EVR over 2 times h. The minus sign cancels, so I have mu 0 EVR over 2 times h. And for V, I substitute m sub L h bar over mass of electron times R. So this is going to be equal to mu 0 E V mu 0 ER over 2. For V, I substitute m sub L h bar over mass of the electron times R times h. So I'm going to see that the radius R disappears from this equation, and at the end I find that the energy is given as mu 0 in parentheses E h bar over twice mass of the electron m sub L times the magnetic field H. So the quantity in parentheses is known as the Bohr magneton. So this is a Bohr magneton. So I can write this energy as mu 0 Bohr magneton m sub L times H. So you can see that in the normal Zeeman effect, due to the fact that I have a non-zero orbital angular momentum, the magnetic moment due to the orbital angular momentum is interacting with the external magnetic field, and that causes a splitting of the energy levels that is proportional to the magnetic field. And so for L equals to 1, the corresponding energy levels would be, we would get energy is mu 0 mu b times h 0 and minus mu 0 mu b times h, and the amount of splitting delta E, the distance between energy levels, is mu 0 mu b m sub L times h. So it's actually, the change in m sub L, which is 1, so it would be mu 0 mu b times h would be the splitting. So the splitting is controlled by the external magnetic field. As I increase the magnetic field, the splitting will increase. So equal splitting in the normal Zeeman effect in the energy levels. Okay, so the energy of an atomic orbital changes in the presence of a magnetic field, and the amount of splitting is proportional to the magnetic field. The energy level that you obtain will be determined by the value of the orbital angular momentum, magnetic quantum number m sub L. So this can be, for example, can be observed in a material where we have no net spin angular momentum. For example, calcium and magnesium will display a normal Zeeman effect. So here I have two remarks about this effect. The first remark I want to make is the following. Now we have the magnetic moment in the direction of the field m sub z, which is minus EVR over 2 using our classical model, we found to be minus E over 2 m sub L h bar over mass of the electron, which we can write as minus Bohr magneton times m sub L. So this is an important result, and the sign is important. So the magnetic moment mz opposite in direction to LZ. So when I say Z, it's the axis on which I'm applying the magnetic field. So that's projected on the field axis. So we have a minus sign here because of the fact that we have electron charge. The electron charge is negative, so we get the minus sign. Now, another remark I would like to make, the second remark. The s orbital, obviously I need a net orbital angular momentum. The s orbital doesn't have one. The s orbital has L is equal to 0, does not split, right? Since it has no orbital angular momentum because L is equal to 0. The other thing is, as a third remark, we will see when we study the anomalous Zeeman effect, which is the more common one, the amount of splitting that we see in the energy levels are unequal. So in the anomalous Zeeman effect, where we have a spin angular momentum that is non-zero, net spin angular momentum is non-zero, the splittings, as opposed to the normal Zeeman effect, are unequal. We will talk about the anomalous Zeeman effect shortly. Okay, so we see an effect of the external magnetic field on the energy levels of an electron, and that is due to the interaction of the magnetic field with the orbital angular momentum of the electron. So it causes splitting of the energy levels, and the splitting is controlled by the magnetic quantum number m sub L, and the amount of splitting in the energy levels is equal. There is no splitting in the s orbital because it has 0 orbital angular momentum, but there is splitting in the p orbital. And this splitting can be detected by measuring the absorption or emission spectrum of the electron. If we have no net spin angular momentum, we have normal Zeeman effect. If we have a spin angular momentum, capital S, that's non-zero, we have anomalous Zeeman effect. The amount of splitting is proportional to the magnetic field. If you recall, the energy of a magnetic dipole moment in a magnetic field is minus mu 0 dot product of m with h in SI, or minus m dot h in CGS. The magnetic moment is measured in EMU in CGS, and it's measured in ampere meter square in SI. The magnetic field is ampere per meter in SI and Ørsted in CGS, and we have mu 0 in SI, which is 4 pi 10 to minus 7 Henry per meter. And from our classical model, where we considered an electron that is orbiting around a nucleus, so we put a positive charge here, and we had an electron that is orbiting around the nucleus with a tangential velocity v. The radius of the loop was r, and we basically find that the current is electron charge divided by the period t, which is ev over 2 pi r. It has a minus sign because of the charge of the electron, and the corresponding magnetic moment on the z-axis, which is the axis on which I'm applying the magnetic field, is ev over 2 pi r, current times the area, pi r square, minus evr over 2. And the orbital angular momentum is quantized. That's why this is a semi-classical model. I'm also taking into account the quantization of orbital angular momentum. And by substituting m sub l h bar for the orbital angular momentum, I find that the energy is given by mu 0 Bohr magneton m sub l h. So we can see that the splitting is equal between energy levels. I have mu 0 mu b h for delta E. So this is going to be mu 0 mu b h. It's controlled by the external magnetic field. However, the energy of the split levels will be determined by also m sub l value. And this can be observed in an element that doesn't have a net spin angular momentum like calcium or magnesium. I made a comment about the minus sign is because of the charge. The magnetic moment is opposite in direction to orbital angular momentum. The s orbital having no net orbital angular momentum, capital L is equal to 0, does not split. So in the anomalous Zeeman effect, where the capital S is non-zero, the splittings are unequal. We will get back to this.